Welcome everybody to this week's Ask an Astronomer live stream. My name is Stefan Heimersheim. I'm a PhD student at the Institute of Astronomy at the University of Cambridge. And today with me I have Maggie. Do you want to introduce yourself for a second?
Sure. Okay, I am also a PhD student at the Institute of Astronomy. I study protoplanetary disks, which are sort of where planets are born around stars. So I like planets.
Yeah, and today we are here to answer all your questions you have about science, the universe, about astronomy in particular. And yeah, just type your questions in the chat, so you can post them in the YouTube chat, in the Periscope chat, or the other streaming services that we're running. Or you can click on a link to slido.com if you don't want to make an account on YouTube. That I will put in the comments in a few seconds. I forgot that. Meanwhile, we already got the first questions. How are supermassive black holes formed? Do you want to say something about black holes, or should I take this question?
You can take this one. You definitely know more about black holes than I do.
Black holes are kind of an interesting topic, so I kind of learn half of my knowledge about black holes I get from this live stream, because I always have to look up the questions. So, okay, so usually black holes grow by accreting matter. So usually we assume that black holes get created initially when a star explodes. So you have a star that's quite large, a few solar masses, at least a bit heavier than our sun. And when it explodes, when it stops its life, first what happens is that the pressure, like the star stops burning, which means the pressure goes down. So the pressure that previously supported the star falls away, and this means the star falls kind of into itself. And then you get a big explosion, and what is left over is a black hole, which is so heavy that it can't support its own mass, so it all collapses into a really small object. And then you get this typical black hole that looks black because light can't escape from it. And now what can happen is, if matter comes close to the black hole, it can also just fall into the black hole. Just as, let's say, a meteorite could fall on Earth, matter can just fall onto a black hole. It's just a bit more extreme in the case of black holes, because they're really massive and really small. And a really huge amount of matter can fall in. There's a limit, though, to how fast a black hole can grow. So when matter falls into the black hole, it emits radiation, so it gets really bright and hot. And this radiation exerts a pressure. So you can think of all the photons from the black hole coming out of the black hole, colliding with the matter that wants to fall in. And this limits how fast a black hole can grow. But if you form such a black hole really early in the universe, you can get to 1 billion or so solar masses today, if you accrete with this kind of all the time at this limit. Alternatively, black holes can also merge with other big black holes to kind of grow even more. So imagine you have two black holes that always grew at the maximum rate, and then they merge. Then you have a black hole suddenly that's double the size. So that's how the kind of most massive black holes get created. So actually, if you look at a supermassive black hole today, it's made up out of at least hundreds of black holes that have merged together in the kind of cosmic history.
It's pretty dope.
Yeah. And we got a few questions on YouTube already.
Okay.
The exoplanets we can observe through thought to be very massive. Is it possible that they are like Jupiter? Okay, so yeah, we are. I think the question is about how the exoplanets are compared to kind of planets like Earth or planets in our solar system. Do you want to say something?
Yeah, well, yeah, sure, I'll talk about that. Yeah, most of the planets that we do observe that we've catalogued so far probably do look a lot more like Jupiter than they do like Earth, because the way that we look at planets, it's a lot easier to see things that are really big and really close to their star than it is to see something really small, like Earth-sized. So we have a bias towards seeing bigger objects. So in fact, we see even super Jupiter, so things that are bigger than Jupiter. But yeah, so a lot of the really big planets might look a lot like Jupiter, except they'd be really a lot hotter than the gas giants in our own solar system, because they're found closer to the star, because they're easier to see if they're closer to the star, because the way that we see them is by tracking how much light a planet blocks out when it goes in front of its star. That's one of the most popular techniques. And if you're bigger and if you're closer to the star, you block out more light. So we're biased towards seeing really big planets that are really close. So yeah, they tend to be Jupiter-sized, to answer the question. But they also tend to be a lot hotter, whereas Jupiter is quite cold relative to the other planets. But we do see some smaller ones as well. But super Earths, things that are a bit bigger than Earth, are like the lower limit right now.
Yeah, that's really interesting. Oh, we got another question. If a collision with of the Earth caused the Moon, and we know that Venus underwent a collision which resulted in its retrograde spin, why is there no moon or ring around Venus?
It's a good question. I'm not sure. I don't know. I suppose it just depends on the collision happening in such a way that the whatever throws off gets captured by the planet. And I guess whatever collision crashed into Venus, whatever was thrown off just wasn't captured. It's possible also that because it's closer to the sun, that any like you say, I think you mentioned like the why don't we see a ring around Venus? Anything that would cause a ring, like icy bits, would be evaporated and turn to just gas before it could form a ring. That answers that.
Yeah, I think that's a good point. Like that, in general, things are often not as easy as we would like them to be. Like our collision, then we get a thing orbiting around it, but it's just there's so many possibilities.
Yeah, you just got to get lucky.
Yeah. At what stage during the formation of the solar system do we start to differentiate between asteroids, comets, and TNO? And which of these are associated with the bombardment era?
I have no idea.
Okay. Yeah, I think so. What's kind of in general the difference between comets and asteroids, and like the various objects in the solar system?
That's a good question. I think it's mainly what they're made out of. So I think I may have this the wrong way around, but I think comets tend to leave a trail behind them because they're made up of ice and dust and also rocks, but the ice is the main thing. Whereas asteroids don't have ice in them, so they don't leave trails. So basically, as a comet whizzes past the sun or whatever, the ice melts and leaves this trail behind it. So that's why it's a comet. But I don't think asteroids do that. I think asteroids are just bare rock.
Yeah, I think I never heard of an asteroid like with water or ice. And actually, that also ties into the next question, which is which of these brought water to Earth? I'm pretty sure that the hypothesis for water is that it's coming from comets, or at least it's definitely not from asteroids because they're usually just space rocks, right?
Yeah,
comets are the fancy things with the tails.
Yeah, but it is worth saying that Earth probably started out with a lot of water as well. Not necessarily that it had to be brought in. Some of it, sure, but it's not like it starts out with liquid water. But early on in the solar system, you have a lot of ices and stuff that get captured by planets, and then they turn into water once it gets warm enough. Would be my guess how that happened. But yeah, basically, most planets will start out with about the same amount of water, gases, and stuff as what would just be present in the solar system in general. But then some planets just lose it all, like because they're too close to the sun, so it evaporates away.
Oh yeah. Like, do you know if there's how much water there's on Mars in terms of ice? Like, is it much less than on Earth? And does
yeah, as far as I'm aware, there's a lot less ice and water on Mars, and that's mainly because it's the atmosphere on Mars has been stripped away,
okay.
and so there's nothing there to hold the water in, for one of a better word, I suppose. So it can just evaporate straight into space. But there is supposed to be still some ice around there. I think mainly in like salts, ices, and stuff. But yeah, I don't know about the composition differences, how much less there is. But considering Earth has a lot of water, probably quite a bit.
Yeah. Earth has quite a lot of water, luckily so. Well, we got a lot of questions. That's great, guys. How does the equation? Oh, I have no idea about this question. How does the equation of planetesimals not violate the second law of thermodynamics? Yeah, I think I don't remember the second law of thermodynamics out of the hand.
Yeah, I'm gonna Google which one that is. I think it's the you can't become more ordered. Total entropy of an isolated system can never.
The entropy one.
Over.
Okay.
Yeah. Okay. This is also one that I hear a lot when people ask about like evolution on Earth and stuff. The second law of thermodynamics applies to an isolated system. So if we just had a collection of rocks in a box, they wouldn't suddenly collapse into a planet. If I just had a box of rocks, there'd be no way for the entropy to increase over time by doing that process. But if I have an entire solar system, then it's possible for some parts of that system to become more ordered while other parts become less ordered. and that's how you don't violate the structure thing. If that makes sense.
Yeah, so we're kind of trading off the entropy to someone else and get more out of ourselves.
Yeah. So it's okay for locally for things to become more ordered, as long as on the whole you do have an increase in entropy. And also, as you as these planetesimals tend to collapse together, the temperature tends to increase a bit. So that would also help to increase the entropy a bit, I suppose, on a local level.
Yeah, that makes sense. Is it possible for a binary black hole merger to produce a short gamma ray burst, and has this been observed?
I'll let you answer that one. That one sounds hard.
Okay. So first of all, like, maybe I should say a bit about like kind of black holes and their merging and all the mergers that we observe. So when like black holes, just as kind of any other kind of heavy objects, if they come close to each other, they can start to orbit each other. You know, like if you have two kind of, I don't know, stars or so, if they come close to each other, like they can kind of get gravitationally attracted, and the same can happen with black holes. Although usually kind of binary system always, or well, almost always get created in one place, so they get born kind of together, because if you imagine two black holes being really far apart and they're coming close to each other, they won't kind of start orbiting, but they will just fly past each other, maybe get deflected a bit, but they have far too much energy to kind of stay together. So usually you have kind of a system of two kind of stars that get born in one big gas cloud, and they're kind of close together from the beginning and orbit each other all the time. And it usually the first one goes supernova and gets to a black hole, maybe the second one also turns to a black hole, and then you have two black holes orbiting each other, they get closer and closer together, at some point they can merge. And the special thing, well, let's say you don't have black holes, but let's say you have neutron stars, then this kind of merging process, when those two get together, of course releases a huge amount of energy, and we can see this as A, gravitational waves, B, as electromagnetic radiation, and we can observe it with like many telescopes. When we have black holes, as far as I know, we didn't observe any electromagnetic counterparts with those mergers, so we can still see more or less the same gravitational waves, a bit stronger because it's black holes and they're more massive. But I don't think we observed any kind of electromagnetic radiation. And mostly this is because the black holes are kind of small. So you have kind of a Schwarzschild radius. So that's kind of the part where that it looks black, where nothing can escape from the black hole. And inside we think you have some object. We actually have no idea what's inside the black hole. But so you just say, okay, those two objects orbit each other, they collide. At some point, whatever's inside the black hole will collide with, well, whatever inside the other black hole. But since this is all happening inside the black hole, none of this information, none of this light can escape ever to us. So we wouldn't get a simple signal out of this. So that, I mean, you could imagine some signals that get kind of, you could say, okay, maybe particles close to the gravitational field of the black hole that are not actually inside the black hole could emit some radiation. But as far as I know, we didn't observe anything that looks like that. So we didn't observe any kind of what we say electromagnetic counterpart, so kind of light counterpart of a gravitational wave event, which we mainly use to find kind of merging black holes. But it would be really cool if we did someday. Here there was just a comment on the thermodynamics part here. There's a lot of thermodynamics is really kind of, it's a challenge to have to always be careful what you look at your system. Like that's always a big thing. Defining
exactly what your system is and what the boundaries of it can really change what your question means.
Yeah. Why is a planet with 5 Earth masses the most commonly observed one? Is this an observational bias, or are they more stable in some way? So I should
mention with high Earth masses, did you say?
About 5 Earth masses is supposed to be the most common one.
Okay.
So also I opened the plot of the kind of mass versus period distribution here, so from the kind of different different detection methods. And yeah, I think this is kind of this observational bias that you just explained, right? So that
it's easier planets.
Sorry, I think your audio just cut off.
Yeah, it's just easier to see larger planets because they block more light.
Yeah, right.
It is also worth mentioning as well, though, that smaller planets are probably more common as well. So although it's easier to see larger planets in general, you can make more of the smaller ones. So it's an interesting combination of those two biases. Well, the making more of the smaller ones isn't really bias; it's just inherent to nature. But yeah, like if you look at the distributions of stars based on their masses, there are a lot more small ones than there are big ones. And I think planets are something similar to that, if I remember rightly.
Yeah, that's. Second. I lost my phone with the questions. Yeah, I have it again.
That's okay.
Yeah. And do we know anything about the star from whose supernova the Earth was formed? Oh, do you want to say something about what the Earth is made out of and the supernova? Well, I mean, we're all made out of supernova stuff, so.
Yeah, we're all made out of supernova stuff. It's not likely that we're made from the supernova stuff of a single star. It's a lot more likely that we're made of the supernova stuff of lots of different stars that have mixed together and produced our sun. So when a planet forms, it forms shortly after the central star. So in our case, the sun has formed. So you have this giant cloud of gas and dust and stuff, and that squashes down and makes a flattened disk. And in the middle, you have the star, and in the outside, you have a disk like a pancake where all the planets are going to form. But it's all made out of the same stuff. So the sun was made out of the same stuff as all the planets were to begin with. But they get different compositions as they form. So whatever the stars that made up, whatever stars went supernova to give the sun its metals is the same stuff that we got our metals from. But you couldn't really talk about a specific star because a lot of things went supernova before the sun came around. It's not that old.
Okay. Yeah, just a note, I just put in the comments a link to slido.com in case anyone wants to ask a question that doesn't have a YouTube account or Google account. You can also go and ask a question there. That will appear here on the right. So just so you know that the option is there. How does a dying low-mass star contribute to the formation of heavier elements?
It's a dying low-mass star.
Yeah.
Are low-mass stars dying yet?
Oh, that's a good point. That's actually a really interesting question. So do you want to say a bit about like kind of how long stars live compared to their masses?
Yeah. So really, the heavier a star is, the hotter it burns. That's one way of thinking about it. So if a star is really heavy, it's going to burn really, really bright, and it's going to burn up all its fuel in a short period of time. So a star like the size of our sun might live, 10 billion years, something like that.
Yeah.
Whereas a star maybe half the size of our sun will live 100 billion years. And a star maybe, 10 solar masses might live like 1 billion years. They basically, the bigger they are, the shorter their lifetimes are. So really low mass stars haven't yet had time to die. But when they do, they won't go out with a bang the same way that big stars do. They'll sort of just fizzle out and slowly just stop burning and just slowly just gets dimmer and dimmer over time.
Yeah.
So, yeah, they won't have the same. It's the big bang and the big explosion at the end of it that really enriches the environment for other stars to form. So really, it's the solar size-ish and bigger that helps to make metal-rich other stars.
Yeah, that's actually. Yeah, I think this is like really if you look at the kind of, if you look at kind of particle physics and nuclear physics, people figured out that if you take atoms and fuse them together, so if you take like two hydrogen atoms and make a helium atom, you gain energy because the helium atom is actually lighter than the sum of the two hydrogen atoms. So actually it's not. Well, it's not two hydrogen atoms. It's two hydrogen plus two neutrons. Whatever. The helium is heavier than the sum of its parts, which is a really nice feature. Which means if you do fusion, you can gain energy, and you can power civilization if we could manage finally to do that, or you can power stars. On the other hand, if you do fission, so if you take really big nuclei like uranium, and you split it into multiple smaller ones, those smaller ones are lighter than the big uranium. Like the sum is lighter than the big one, so you also gain energy in that direction. And the basic rule, more or less, is you always gain energy when you go towards iron. So combining stuff, like fusing light stuff to iron gives you energy, and fissioning, like destroying heavy stuff to iron also gives you energy. So if you want to produce energy, all you can do is go up to iron, which is why the normal fusion reactions in stars that kind of produce energy only can give you elements up to iron. So that's kind of, there exists like a nice table that I also have open here on the slide that kind of shows you what elements are made in stars. And in particular, the elements, I think it's carbon, nitrogen, oxygen, are made a lot in stars because they're kind of a part of a cycle that goes on, like in their fusion reactions. So those elements are like made a lot by all stars, also low mass stars. But everything essentially above this, you need some chaotic reaction where just everything gets created, and therefore also the big things. And they're like, I mean, mostly I think it's supernovae, but they're also, of course, like if you have merging neutron stars or something, they also produce whatever you want, like essentially everything.
Yeah. If you want to get like things like uranium or gold, you need supernovae.
Oh, yeah, we have a question about why some heavier elements, such as thallium, are more likely to be produced from dying low mass stars than from neutron star mergers.
That's a good question.
I don't think I don't know. I know that many details. Yeah.
Can you repeat the question?
Why are some heavier elements, such as thallium, more likely to be produced from dying low mass stars than from neutron stars?
From dying low mass stars than from mergers, did you say?
From neutron star mergers.
I do not know, but one reason at least I would imagine is I can't imagine neutron star mergers are as common as stars dying. That could be a contributing factor. But maybe they are.
Yeah, I think it's probably related to kind of what the kind of processes are doing this process, doing the kind of merger or the dying of a star, so that the energy is just right to produce certain elements. So if you have just really high energy, then of course you will produce equal amounts of everything, well, not equal amounts, but you'll produce kind of everything. But let's say you only have like half the energy that you need for let's say you only have energies up to, I don't know, rubidium. Then you'll probably only make elements up to rubidium, and a lot of them, and no kind of bigger elements. So kind of if you have a process that's kind of tailored to the energy of an atom that you want to produce, then this is usually more likely. But in the particular case of this, like dying low mass stars, I think we're both not experts, so we don't really know the details there. Okay, how do we determine the regional distribution of different elements in a protoplanetary disk? What's the average number of planets formed in a protoplanetary disk?
What's the average number of planets formed in protoplanetary
Well, yeah,
disks?
let's start with this one.
Okay. I have no idea. I know that most stars have at least one planet. I would expect there are probably a lot of protoplanets, a lot of small baby planets made in the protoplanetary disk that are then like lost or crash together or just fizzle out for some reason before you settle on your actual end planets. The question of like an average number probably just depends a lot on what conditions you're looking at. That's not very satisfying as an answer, but I don't expect there is an average number beyond just tallying up how many. I mean, if you want the average number of planets made in a protoplanetary disk, you can just find out what the average number of planets there are around a star, because those will be the same answer.
Yeah, okay. Yeah, I guess we can look up the number afterwards at some point, and then I'll add a comment to the chat for the correct number. But yeah, I think also one thing I would note is that if you try to find planets, you probably are more likely to kind of, well, actually, I don't know. When you look for exoplanets, do you, like, let's say you find a planet in one system, do you pay closer attention to that system and do extra observations, and then maybe find more planets in that system? Or is it just surveys that just look at every planet star anyway?
I think it might probably depends on how the planet was found in the first place. I know, for example, let's say if you found a system and you found 2 planets in that system, and you were pretty sure that there were 2 planets there, then that system would probably be like fairly well analyzed because people are interested in how planets interact with each other. And so then you're probably more likely to find out if there are more in that system than not. But people are excited when they find multi-planet systems. So I'd expect if people thought there were many that you could detect in a system, they'd pay close attention. An example of that would be the TRAPPIST-1 system from a couple of years ago, where they found, I think, 7 in one system. And these aren't exciting because we think having a lot of planets around a star is rare. They're exciting because we think being able to see a lot of planets around a star is rare, which is very different.
Oh,
So planets are hard to see.
why is it harder to see if you have many planets in a system?
It's hard to see small planets, and it's hard to see planets that are far away. So if you think you've got a star here, there's a certain radius around that where you're likely to be able to see a planet. And if it's further away than that, then it doesn't block enough light. It'll be too dim unless it's really, really big. So really, you need to have a lot of planets formed like quite close together to be able to see them. But yeah, it's basically just the odds of there being enough planets of the right size and close enough to their star that you can see them makes it hard to find multi-planet systems. But we think there are probably quite a few out there. Yeah, and hopefully as we push the boundaries of how small the planets are that we can see, we'll find more.
Yeah. Yeah, we got also one question about kind of the how do we determine the regional differences in protoplanetary disks with respect to, what was it, what kind of elements there are. So yeah, like what kind of elements are there in what region of the protoplanetary disk? That's a really terrible word. So, like, do we direct observations with telescopes?
I think it's where, broadly we determine those based on how hot that part of the disk is, and we say if the temperature here is low enough that this element would or this compound would be ice here, then it's present and it can form like in a core, and it doesn't need something big enough to trap it gravitationally. So basically, if you say that if you're really close to the star, say where Mercury formed, then it's too hot for liquid or ice water. It's too hot for most gases or most things that are gaseous on Earth to be liquid or solid. So really, the only things that you're expecting to be solid and able to collapse into a planet really close to the star, like Mercury's own, is things like rocks and metals. And if we look at the composition of Mercury, it's mostly rocks and metals, so that makes sense. Then as you move further out, you move out to say where Jupiter is. You pass what we call like the snow line, where liquid water and ice water can form. Because it's cold enough, you're now far enough from the bright hot star that you're cold and you can form ice. So now you can say once you're out here, you can have solid rocks, you can have solid metals, and also you can have solid ices. And that's why you can collapse all of those together and you can make bigger planets, because now there's more stuff that's solidified. So basically the regions are just determined by how hot things are, pretty much.
Okay.
That makes sense.
Yeah, and so when we have this protoplanetary disk, we now start out with a kind of a big cloud of dust or with a big cloud of material. And how long does it take from there to kind of go to something like our solar system? So to kind of get...
Well, I know protoplanetary disks last for maybe 10 to 30 million years. I'm not sure how long it takes from like a giant cloud of gas to the protoplanetary disk being born, but I guess a few million years, something like that. Maybe shorter. I don't expect that to be a very long-lived phase once it starts. But yeah, basically, once you've got your disk of stuff, between that and it being cleared away by the solar wind or by just being evaporated by the strong light that you've got going on, it's about between 10 and 30 million years ish. So it's I mean, compared to the lifespan of a star, it's very quick.
Okay, that's nice. And we got one question. What do we actually mean when we say that a star could not hold itself together and imploded under its own gravitational force to form a neutron star? So for that, you kind of have to understand, like, stars, essentially they're not that, like, then they're not solid in some way. They're just like big balls of kind of burning gas. And there's not really some material or so stopping more like the gas from falling further into the star, but it's the star kind of the burning itself. So what happens is in the center of the star you have the highest density, and there actually the fusion happens, at least in the kind of normal phase of a life. Correct me if I'm saying something wrong. And so in kind of the core of the star, you're doing fusion and you're producing loads of energy and loads of photons, and those photons get where they fly out of the star and they create a pressure. You can just imagine this just when you're kind of driving over on the, like, let's say the highway, like all the air molecules are let's say, like, I don't know, colliding with your car or with you, depending on what kind of vehicle you're driving. So you get kind of the exerted pressure on you. And the same happens in a star when there's material around the star and the photons come out, so they exert a pressure. And this pressure holds against the gravitational force of everything that wants to fall into the star. So you get kind of this equilibrium. And when the star stops burning or starts burning less, this pressure goes down because there are less photons flying out, which means the stuff can kind of collapse more, can fall more into the star. And when the star has burned up all of its, like hydrogen and helium and other things that it can fuse, then there's nothing left that's burning, so nothing holding the star kind of from inside, nothing is holding the star up, and just everything falls together. And then you get, then you get kind of a shock-like increase of density because suddenly everything is falling together. I'm not familiar with the details of how like supernovas and explosions work, but I think essentially you get some kind of explosion, and either you can get something like a red giant, where the star like blows up like to a huge version of its former self. So for example, in the case of the sun, the star would be as big as kind of the orbit of the Earth or even Mars, depending on what model you calculate. And or you could get kind of a supernova, so a really kind of strong explosion, where something in the center is left over, that's the black hole, and a lot of mass is kind of just thrown away. Yeah, so that's kind of, I think, what we mean by like when it implodes. Holding itself together, I think, is kind of a misleading metaphor. It's more like it can't hold itself up anymore.
Yeah, it can't support the upper layers anymore, and they just squash down. And I suppose to address why that then makes a neutron star, when they squash down so much that that a normal gas wouldn't be able to support that density anymore. You need to have a more degenerate core than is possible, because electrons can't occupy the same space, say. That's like a quantum physics thing. If you squash like lots and lots of electrons really, really, really close together, they're not able to exist in the exact same point in space, whereas neutrons can, or can pretty much do that. So basically, neutrons can squash a lot tighter than electrons and protons can, mostly because of the electrons. And so that's why you get a neutron star at the end, just to add that on to maybe explain that bit.
Yeah, that's really nice. We just got one question on Periscope, although it just disappeared from my screen again. So if you could just ask it again, or in case you deleted it, that's fine. I'll check the settings to make sure they don't disappear again. And while we're at that, let's continue with the next YouTube question. We got our daily alien question.
I love alien questions.
Oh, that's great. Okay, so we got a question about if it's possible that they are aliens, or, well, did you see any evidence of aliens in your lifetime? And what's in general, what's your thought about extraterrestrial lives?
I've never seen any evidence of aliens. I'm not sure that there is any evidence of aliens on Earth at the minute, but it's almost certain that there is extraterrestrial life out there somewhere. Just because, as I mentioned earlier, most stars have at least one planet, and most stars, in fact, probably have more than one planet. And statistically speaking, some of those planets have to be Earth-like. They have to have liquid water. They have to be the right temperature that it's possible for life to form. And basically, we have no scientific reason to think that we're unique and that we're the only place where life could ever form. So it's probably out there somewhere, but the statistics also mean that it's probably far away, because space is really, really, really big. So I think aliens are out there, and I think they're really far away. Is my thoughts on that.
Okay. So we got the question on Periscope again. How do we differentiate BTN, transitory objects, and cyclical dimming of stars when looking for planets? Okay, so I think the question is like when you could have, when you see a star dimming regularly, you could have either some object rotating, like flying around it, like a planet, and making it dimmer every orbit, or you could just have a star that has some kind of cycle that makes it dimmer periodically.
Mm-hmm. Yeah, that is a problem. It's hard to work with. I'm not an expert on observational junk, but there are there are certain behaviors that I know that can be mixed up for planets and how to get around them. So things like sunspots. If you look at the star for a short period of time, seeing a sunspot track across the surface, say as it spins around, that can be confused for a planet. But sunspots also aren't like permanent; they're transitory. And so if you look at it again in a few months, then you won't see that anymore, or you'll see a different sort of feature. So basically, when you look at exoplanets, you expect the signature to be constant in time, or pretty much constant in time. And it can be difficult because it can be overlapped with those transitory features, but there should be something that's constant. And I don't think most star cycles are typically non-variable. I think like something like the life cycle of the sun, say, varies over the course of like 22 years. But I don't know much about cyclical stars. So.
I think one thing that I'm sure you can use is that kind of when a planet goes in front of a star, you know pretty much exactly how the signal is supposed to look like. So you know that, well, you have kind of a normal star brightness, then it kind of goes down while the star, like planet moves in front of the star, and then it's kind of like constantly a bit lower, like while the star is in front, the planet is in front of the star, and then it goes up again when it moves out of the star, and then it's like normal for quite a long time until it goes in front again. So like this is a really precise shape. Like it has to be flat, 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 go down, flat, flat, go up, flat, 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 and kind of getting exactly this with a cyclical feature. It does work with a like solar, like if you have a sunspot, but it doesn't work with it doesn't work with most kind of cyclic star things processes. So they usually should give you other features. But of course, if your telescope isn't perfect, which telescopes sadly are not perfect. Still have to work on this. Then of course you can't like perfectly distinguish between those options. So of course you always have some like. If you have very good observations, it's easy. If you have not so good observations, it's harder. That's kind of the gist of it, I guess. So we got a lot of YouTube questions. Can you tell us more about the solar wind?
More about the solar wind?
Yeah.
Sure.
Yeah, then go ahead because I can't.
Okay. So the solar wind is just a bunch of ionized particles. It's a bunch of charged particles. So you've got electrons, you've got protons, you might have some alpha particles too, so some helium particles going on as well. And basically at the surface of a star, it's very hot, and it wants to push stuff out into space, pretty much. Because if you think about, it's not a perfect analogy, but hot gas exerts a pressure. So if you think of like hot air rising and exerting a pressure against the cold air around it, basically you've just got hot air exerting pressure and blowing stuff out into space. And it moves pretty quick. So yeah, basically the solar wind is just a bunch of ionized particles, a bunch of ionized particles plus their electrons, blasting through space and hitting stuff. If it hits the Earth and our atmosphere, we've got a magnetosphere, so we've got a bunch of like magnetic loops coming around our planet, and because the particles are charged, that can like deflect it and so protect us a bit. But if you don't have a magnetosphere because you haven't got a properly differentiated core, say, then and you're something like Mars, then instead of deflecting on your magnetosphere, all these particles strike directly into your atmosphere, and so they can strip it away. And that's why Mars hasn't got an atmosphere anymore, and we do.
Oh, okay. So yeah, let's keep that magnetic field, please, then, because I like our atmosphere.
Yeah, we like having an atmosphere.
Now we got a question about galaxy evolution. Why does the center of which galaxy clusters consist mainly of elliptical and lenticular galaxies as opposed to spirals? Do you know how kind of galaxies evolve between like from kind of spiral to elliptical and things like that?
No, I know very little about galaxies.
Yeah, same for me. So let's see what we can piece together. So I know about galaxy clusters. That's my field, more or less. So like you have galaxy clusters are just really big. Like there's a kind of areas in space where there's a lot of matter. So there are kind of a lot of galaxies that are all really close. Well, kind of all gravitational bound, and they're kind of all flying around the same kind of big gravitational point. And usually you have, well, at least the question asked told us that in the center you have a lot of elliptical and lenticular galaxies, and spiral galaxies not so much, right? Yeah. Yeah, so I think spiral, like usually galaxies when they're young tend to form spirals. I think it's like related to what kind of what's the gas content or something of the galaxies. So if you have lots of gas or not so much gas, it can form stars in the galaxies. And older galaxies tend to kind of evolve towards kind of more elliptical galaxies. Although I'm not sure why, why the older galaxies would be more in the center of gravitational of galaxy clusters. Yeah, do you know if there's like any effect that's relevant?
Why the older galaxies would be in the center of galaxy clusters?
Yeah.
No, I don't know.
Okay, yeah, I will just send this question to the next week and organize someone who can tell us about galaxy evolution.
Get a galaxy expert in.
That's what we do here when we don't know the answer. Okay, which is more likely, that a planet has a moon or it doesn't have a moon? Oh, that's a cool question.
That is a good question. Let me think. I think this might depend on your definition of a moon.
Okay.
So if you just say, is it more likely that a planet has satellites orbiting around it than not? I think yes. I think most planets probably do have some kind of satellites orbiting around, especially most big planets. Mm-hmm. So like further out, because more stuff solidifies and more stuff gets crashed into it and captured. But whether those things tend to be big enough to be considered what like most people might call a moon, I'm not sure. Because if you think like Earth has our moon, and I think there's also something like 100 or so like satellite objects that are, fairly large and not inconsequential, that maybe if we saw them on another planet we might call moon-like objects. Yeah, I think most planets probably have satellites. I think most big planets, so like Jupiter size, say, probably have things that are big enough that they're round and so they're moons. But I wouldn't be able to answer on the proportion of smaller planets to have like round moons.
Yeah. I think like when I look in our solar system, it's like I don't think we have that many observations of moons from kind of outside of the solar system, if any.
No, they're very hard to see.
Yeah, I mean planets are hard enough to see. But yeah. I mean, looking into our solar system, I think everything bigger than Earth has a moon. Like, right? Does Mars have a moon?
Does Mars have a moon?
Oh,
I'm really bad at solar system planets.
That's theoretical astronomers for you. Does Mars have a moon? At least Jupiter has tons of moons. Saturn has tons of moons. I think Neptune.
Jupiter has tons of moons.
Uranus also
I think Mars.
Moons.
I think Mars does have moons. I'm pretty sure it does. I think it's got a couple.
And Pluto also does, and well, Earth obviously does.
Pluto is debatable because some people would call Pluto's moon more of a twin planet than a moon. But
okay, but that's, I mean, before you argued it might be too small, now it's too big. Like moon people are really kind of strict in their criteria, I guess. Okay.
Yeah. Yeah, it's hard. It's a hard thing to define.
There we go. Thank you for the comment. Demos and Phobos, of course. Yeah.
Oh yeah, I know the names. Thanks.
Mars does indeed have moons, and that's at least the second one name is the one I actually know.
Yeah, I've heard. Yeah, I know them now that you've mentioned the names. Yeah, it's really. I don't think there have been any observations of moons on other on planets outside our solar system. There might be, then I could be wrong about that. I'm not very good at observations, but yeah, the thing is, it's very, very hard to see. It's already hard to see planets around other stars, and to see a moon, rather than looking at like a blip that the planet makes as it orbits the star in the middle, now you're looking for like the even tinier blip that the moon orbiting that planet would make as it orbits the star, which would also have like an even funnier period as well. So it's just a hard thing to see.
Yeah, we got another question. Actually, yeah, we got another comment on YouTube. So both of our chats quickly replied with the number of moons. Thanks for that. With the fitting name, Pegasi51. So now we have a question. What is more likely timeline for a planet like Earth versus Mars? how come Earth did not lose its atmosphere even though we are exposed to the solar wind too?
Yeah, so that is a consequence of the fact that we have a very strong magnetic field, and sometimes it's just a consequence of just luck and how things transpire. For example, like Venus doesn't have like an intrinsic magnetic field either, but it's got such a thick atmosphere to begin with that when the solar wind hits Venus's atmosphere, it ionizes the top of it, and so now you've got it gets this like induced magnetic field that protects it because it's been ionized. Earth has its own intrinsic magnetic field, so we're safe. Mars, I guess, never had a thick enough atmosphere for it to have an ionosphere. An induced magnetic field caused by the stellar wind. Yeah, so we're protected because of our magnetic field. Venus is protected because of its induced magnetic field, and I guess Mars just didn't have either of those. Or maybe it did at one point, but some blast knocked it off.
Do you know anything about if it's like how likely it is if a planet forms, how likely it is to have a magnetic field? So if planets usually have a magnetic field?
I'm fairly certain it's to do with the core of the planet. Now, I'm not sure if it needs to be a molten. I think it does need to be a molten core. First of all, it needs to form slowly enough that it becomes differentiated. So by that, I mean it needs to form in such a way that the core of the planet is made of different stuff to the outer side of the planet, such that heavy stuff settles down into the core, and so you have a core made out of metal. And so if you have a core made out of metal and it stays hot for long enough that it's molten, so something like Earth-sized, then it moves around, and that's what causes our magnetic field in a very rough way. I'm sorry to any like geologists watching. That's roughly what's happening. So if you're too small, like you're like Mercury-sized, your core doesn't stay hot enough long enough for it to differentiate and for you to have like a molten metal core and to make a magnetic field that way. So I think anything like Earth-sized and bigger, has a good chance of having a magnetic field, I'd say. But I'm not an expert on it.
Okay.
Yeah, but I think if you're big, you've probably got a magnetic field of some form.
We got a few questions on Slido. So we have the question, is it true that Andromeda Galaxy is moving towards us?
Okay.
So do you want or should I?
You can go.
Okay. Yeah, that is indeed true. That's the easy answer. The more elaborate answer is, so what we can do is we can measure the so-called Doppler shift of objects in Andromeda. Mostly this Doppler shift. So when you look at a certain frequency of stuff in the Andromeda Galaxy, so let's say you look at some emission lines of some elements or something, and you can see what that frequency should be from measurements in the lab or from our own star or our own galaxy, and compare them to what you measure. And from that you can infer how fast Andromeda is moving and in what direction. It's similar to the effect that you know from more or less everyday life. When you have an ambulance or a fire brigade truck driving towards you or away from you, you hear them as slightly different sounds. Because sound waves are traveling away from moving objects, and that makes them longer or shorter. And the same works for light waves, so that's the effect is called Doppler effect, both for light and for sound. And this changes the frequency of all the light that's arriving to us from Andromeda, which tells us in what direction it's moving. And that's actually a special thing. So most galaxies are moving away from us, which is related to the expansion of the universe. Only Andromeda and a few other galaxies are actually moving towards us. So in many billions of years, many years, we will be pretty alone in the universe with our Milky Way together in the local group. So we will be together with Andromeda, which will have merged with Milky Way by then. And I think the Magellanic Clouds and maybe some other smaller galaxies. So that will be our group, and everything else will be expanding away with a high velocity and eventually be unreachable for us. But let's move to a heavier topic. Time was moving at zero speed at the Big Bang, so has it been speeding up ever since? That's an interesting question. So I think the concept of time moving is really hard to define. Um, so because, well, I mean, if you want to see how fast is time running, you have to compare it to something. And you can't just go with a stopwatch and compare how fast time is because, well, time is the thing that makes the stopwatch work. One thing you could do is like kind of compare it to how fast the universe is expanding. So you could say in the very early universe, time was running slowly, or you could say the universe was just expanding really fast, and the time was, well, you could say the time is normal, and the universe expanding really fast, or you just look at how fast the universe is expanding and take this kind of as a reference, and then time seems to run really slow. So, for example, the whole inflation stuff happened in a fraction of a really small fraction of a second. And even the whole synthesis of all the elements in the universe, so all the helium, all the hydrogen, a bit of the lithium, was created in the first kind of 3 minutes after the Big Bang. So this was stuff that happened in minutes. Like half of what I learned in school, like in my cosmology classes, happened in the first few minutes of the universe. Even the cosmic microwave background was emitted 380,000 years after the Big Bang. But then there were 13 billion more years where essentially, well, also stuff happened, but not that as much as in the beginning. So yeah, the universe was really hectic at the beginning. Lots of stuff was happening in a very little time. So yeah, and afterwards, kind of, the universe worked much more slowly. So the time kind of appears to, be less of a. It's kind of less hurried now. We got one question about. Oh, we've got a kind of a career question. So, if you want to become an astronomer, what things in general do you need to know?
I guess this depends on what country you're from, partly. If you want to become an astronomer, I think the route that most people take where I'm from is they go and they get a physics degree to start. And I mean, I started out in a general science degree. So I finished school and I liked maths and physics. So I went into a general science degree. And then I specialized into astrophysics towards the end of my undergraduate degree. And that's how you get a degree in astrophysics.
Yeah.
Yeah, I guess if you do want to become an astronomer, and not just like an amateur astronomer, even though that's a lot of fun too, if you want to study it and as your job, maybe put a lot of focus into maths and physics, is what I would suggest if those are options for you.
Yeah, I think like a good bit of math is something you always have in like most kind of sciences, and then yeah, like I think it's rare that you can actually like study astronomy or astrophysics in the university in the beginning. So I think in all the universities I looked at in Germany, in almost all of them, you had to study physics. There was no astronomy degree, and you could then later specialize. I think that's that's probably a good thing. So you can kind of explore different options. But yeah, maybe I should say this also. Like the most important thing is that you have fun what you're doing. Like if you have fun learning astronomy and you have fun like doing the math and the physics that's like necessary for astronomy, I think that's a really good base to kind of learn astronomy. And
if you just like space, you don't need if your thing is that you really love space, being an astronomer, being an astrophysicist, that isn't your only option for getting into that field. Like I know people who work as engineers, which is also math heavy, I suppose. But I know people work as engineers working on rockets and stuff. And I also know a space lawyer, so she works on sort of patent law for people looking at going into space and what can they own in space. And so she doesn't know much about math or physics, and yet she gets to work on space in her day-to-day life. So it's not something that if you really love space, but maybe that doing math and knowing about physics isn't your passion about it, there are other routes to take too.
We've got another YouTube question. Are protoplanetary disks classified into different categories? And if so, on what basis?
Yeah, so protoplanetary disks are categorized based on, I think it's the YSO system. Let me double check that is specifically about protoplanetary disks. Yeah. So that they're classified based on what the light that they emit looks like. If you think about the stages, they're basically classed based on the stages of formation, based on how early on they are in their evolution. So if you think of a giant cloud of gas before the star has formed in the middle, or maybe just as it's forming in the middle. You don't see much of the light from the star in the middle. Most of what you see the light from is from the gas around it, because it's just covered in clouds. And so you might not see what you'd expect a star to look like. Instead, you see what a giant cloud might look like. Then as that gas gets cleared away, you start to see more of the star and less of the disk. And that's how they're categorized. So if you can see a lot of this, all you can see is a giant cloud, then you're looking at a young stellar object of like class, I think it's 0. It might start 1 or 0, the first class anyways. And then as that cloud is blown away, and as you just have the disk left, then you have the next class. And then eventually that disk is blown away and you're just left with planets. And that's your final class, basically. So it's basically just how far along in the evolution there is. Are you a giant cloud of gas? Are you a star with a disk? Or are you a star with planets? Is how they're classified. And that's young stellar objects, if you want to Google it.
Okay. I think we got a follow-up question to our discussion about studying. We got a question about what countries we are from and how many PhD students there are at IOA.
Okay.
Yeah, so, yeah, go ahead.
Cool. I'm from Ireland, and I think there's 16 students in our year at the IOA.
Yeah. So I think what I would like to say, like, it's kind of, I mean, the astronomy is like the IOA is like one department at the university.
Oh yeah.
But there are like actually multiple departments working on astronomy in the broad sense. So there are a lot of people having physics PhDs or math PhD. I think it's math PhD that they're doing. They're also working on cosmology, which is kind of a part of astronomy. So they're kind of multiple fields working together on this topic. I think our PhDs are both on astronomy directly, at least officially. And I mean, of course, there are people doing a math or a physics PhD, and I'm doing astronomy PhD technically, but we're essentially doing the same physics, so it's not that kind of important. Like I think kind of your topics probably might define more than actually what is it saying on the degree. And actually, oh yeah, I should say I'm from Germany, so I did my master's in Germany, and actually also like regarding the German system, I think also like if I had done a PhD at that university, I would be doing a PhD in physics, and I would be essentially doing the same because I'm doing like kind of this topic all the time. So yeah, that's just kind of what degrees your university can give you.
Yeah.
Order and change of physical states started after the Big Bang. So the entropy has given rise to time and changes matter. Oh, that's a good question. 1 second, I have to read everything. Time itself started with the Big Bang and you lead to positive entropy for the forward flow of time and negative entropy. Okay. Okay. So this question is about kind of if like what time itself is and well, it's how it's related to entropy. And yeah, this comment is saying that kind of time started with the Big Bang. I think it's really hard to kind of scientifically say anything about before the Big Bang, or actually about the point of the Big Bang itself. So I think you can make this kind of argument of, okay, we define time as the thing, like we define time as oriented in like as a reference. We look at entropy, so how the order in the universe evolves, and it gets less and less ordered all the time. And that's why you could say, okay, this is the direction of time running into. Like time is always running in the direction of increasing entropy, so less order but less structure. Actually, well, I should also say this thing when we talk about entropy and we say entropy means less order and less structure. The universe got more structured all the time. Like the universe started out as a big hot soup of well, hot gas, and ended up with like planets and galaxies. But it's always about this thing of what we discussed in the beginning. You have to look at the entropy kind of globally and over the whole universe. So yeah, I think kind of how the universe started, like if time started with the Big Bang, or also a question we got before on Cybo, what came before the Big Bang, is not really, like there are some theories that like discuss stuff before the Big Bang, although then the Big Bang is usually not the beginning of the universe, but there was something before. So we can't really say anything about the beginning of the universe. Well, we can't say anything about before the beginning of the universe, let's say it this way. So, that message just got deleted, never mind. Yeah, that's, I think, a difficult question to talk about stuff before Big Bang. And yeah, also the thing like backward negative entropy backward time, that's yeah, relatively kind of complicated, and I think there's not much, well, at the moment at least, there's not much kind of physical meaning behind looking at things before the Big Bang or universe going backwards or time running backwards. But yeah, it's interesting to think about. So we also have, we are at 8, well, depending on your time zone, we are at 8 p.m. in my time zone and 7 p.m. in your time zone. And so we should come to a stop now. And I think we answered all the questions at the moment. So that's a good point to stop before more questions start coming in. So thanks everyone for tuning in. Thank you, Maggie, for giving all those great answers.
Cool. Thanks for having me.
And yeah, actually I could maybe put up, we're just going to comment on the PowerPoint. I might be able to put the PowerPoint slides somewhere online in the future. I'll update you on this. And yeah, thanks again for all the viewings and all the chat comments. Like, it was great with you. You had loads of questions. We will be back next week on Monday again in the evening on all those channels. You can watch us and ask questions. You can also ask questions beforehand. There's a website linked up here, actually. On top you see our website, where you can also send questions beforehand if you want. And if you want us to prepare a question, actually. And actually, there's also some program going on this YouTube channel over the week. So I think Matt Bothwell is doing a live stream. So if you want to tune in there, you're welcome. And yeah, thanks again, and have a nice evening or day, whatever time zone it is.